continuous compound interest. So in this video I will try to work out the solution to the investigation which is part of your textbook. So here it's just the PDF copy of it. What I do, I go step by step through it and try to work it out. Perhaps best way for you how to work out this investigation is to try it yourself. Try it without watching this video, and if you are not able to continue or if you are stuck, just then it's perhaps best to watch the video. But don't watch the video before starting this and trying it yourself. Okay, so let me start. A formula for calculating the amount to which an investment grows is U sub n equals U sub 0 times 1 plus I all to the power of n, where U sub n is the final amount, so the amount that you get when your investment is mature. U sub 0 is the initial amount of the investment, the money you put into your account or into the bank. I is the interest rate per compounding period, and this is important fact. I is the interest rate per compounding period, and n is the number of periods or number of times the interest is compounded. Compounded, it means added to your value or to your balance of the account. Okay, we will investigate the final value of an investment for various values of n and allow n to get extremely large. Okay, so what to do? Let's start with part 1. Suppose $1,000 is invested for 1 year at a fixed rate of 6% per annum. Per annum means per year, so it's 6% per year. Use your calculator to find the final amount of maturing value if the interest is paid. And now we have 6 different scenarios. So in the first scenario, the interest is paid annually. So it means that the number of compounding the number of periods that the interest is compounded is just 1, and the interest rate per compounding period is 6%, which is then converted to a fraction 0.06. Okay, now I will not use the calculator in this, but instead I will try to work with Geogebra. So let me go to the Geogebra, and this is what you get when you open the Geogebra Classic. And what I need now is I want a spreadsheet, and I do not want this graphical window here, so I click here and choose View, and I'll just remove graphics from the view, okay, like this. Now, what I need is the following. Here, this column will be representing U sub 0, so this is the initial amount. Then I will need n, the number of times in which the interest is compounded, and I, which is the constant per 1. Well, I need to use this to write it correctly. And finally, what I have is U sub n, so it's the final value of this investment. Now, what I invest is $1,000, so let me have it here. And now, in this first scenario, the number of times the interest is compounded is just 1, and the interest rate per 1 compounding period was 6%, so it's just 0.06, like this. And now the formula for U sub n should be, I will use the equals sign, and what I need is to use this number, which is A2, it's the cell with coordinates A2, times, and now using the formula for the interest, it's 1 plus, and for I have the formula C2, okay, and all that which is raised to the power of n, which is in the cell B2, like that, okay. So what I get is the answer of $1,060 after 1 year in which the investment was compounded only once, and the interest was compounded only once, and the interest rate per annum was 6%. Now, in part B, we have to do it quarterly, so it means 4 times a year. But if you do this 4 times a year, and you know that 6% interest is per annum for a year, it means that for each compounding period of a quarter of a year, you have to take the interest, which is 1/4 of the interest per year. So instead of taking I equal to 6%, it's going to be 6% divided by 4 this time, and therefore it will have the effect on the answer. Okay, so let me return here. What I do now is I take this and try to copy it down, okay, like this. And what I can do now is to change parameters. So in this case, I need n equal to 4, because what I do is I repeat this process of adding interest 4 times per year. But instead of having the I equal to 6%, I will decrease it dividing it by 4, like this. And you see, it has the effect on the answer. The answer is changed. So instead of having $1,660 at the end of this year, I have a little bit more. It's 1,061.36. Okay, now in part C, I have to do it monthly. So when I do it monthly, well, it means that n is 12, because I do it 12 times, and the interest rate is 6% divided by 12. Okay, so this is what I know. Let me set it here. So I will set the number of times that the interest is compounded to 12. Now the value of 6% is going to be changed. It's going to be this divided by 12, because I have to divide by the number of periods. And you see what I get as the result. Now, the problem here is that Geogebra tries to evaluate all the numbers to 2 decimal places, so therefore it's time for me to go to settings and change it. Instead of 2 decimal places, let me use, let's say, 5. Okay, so let me close this. Now you see that the interest per compounding period was just 0.005, and the answer is very close to the previous one, but it's more, a little bit more. Okay, so this is part, or the scenario C. Now in scenario D, we have to do it daily, so we have to compound the interest daily. Therefore n has to be number of days in the year, so it's 365, and I has to be 6% divided by 365. So each time we add the interest, it's the interest rate per compounding period is going to be this. So let me move back to the table and input these numbers. So number of compounding periods is 365 this time, and this is reduced, it's divided by the number of these periods, 365, like this. And what I get is the answer, and it's $1,061.83. So it's a little bit more, a tiny little bit more than when I compound it every month. Now let's move on. The next part is by the second. Imagine the interest is added each second. So the trouble here is what to take as n. So we need the number of seconds in a year. So I'm going to use the calculator this time. So I know that there is 365 days in a year. Now I multiply by 24, which gives me the number of hours. And each hour has 3,600 seconds. So if I multiply it by 3,600, what I get is a stupendous number. And that number is the following. It's 31536 and 3 zeros after that. So I would say it's 31,536,000 number the times. So this is the number of times the interest is compounded, and therefore I should be 6% divided by this number, 31,536,000 times. Okay, so let me use this for the calculation here in this table. So the number of times that I am going to use this is 31,536,000. Okay, like this, and this number here is going to be divided by it. So 3 divided by 31,536,000, like that. And you see, you get, well, in the almost indistinguishable answer. If you do it every second, you also get $1,061.83. There is just the difference in the tenths of a cent. Okay, now let's go back and look at the final scenario. The final scenario, we have to compound the interest every millisecond by millisecond. So the number of compounding periods is even 1,000 times more than before. So n this time is going to be 31,536 and 6 zeros after that. Also I is going to be 6% divided by this great number, 31,536 and 6 zeros after that. Okay, so let me get back to this and do it. So here the number of compounding periods is going to be 31,536 and 1, 2, 3, 4, 5, 6. So we have 6 zeros in total, and this interest rate per compounding period is going to be this divided by 31,536 and 6 zeros after that. You get this answer here, and you see that, well, it changed a little bit, but this time I would not be very much sure about the fact that it's less than before. This perhaps means some rounding errors in the engine of Geogebra, because the answer should be increasing all the time, but it should approach the final value. So now in part 2 of what to do, we should comment on our answers from 1. So what we saw was the following. We saw that as we increased the number of times we compound the interest, the final amount increased, but it didn't increase equally. It increased in such a way that it approached a value. It approached a value of $1,061.83 and something. Okay, this was the value approached. Now this has some meaning, and perhaps if we continued like this and had a better calculator than the Geogebra has, we would get the limit, the number to which it tends, and would be able to express it. And this is what we want to do in what follows. So now in part 3 of this, let us look at it and work on it together. So if R is the percentage rate per year, so in our case it was 6%, T is the number of years, and N is the number of interest payments per year, then I has to be R divided by N. So you saw that this really works. So if R was 6% and we had N, for example, 12, what we did, we divided 6% divided by N, and we got the interest rate per compounding period. Okay, N this time is the capital N because it's the number of compounding periods per year, while here the small n was just the number of compounding periods in total. But incidentally, we had just 1 year, the time of 1 year in parts A, B, C, D, and so on. So let's get back. And now n, the total number of compounding periods when you have to wait for t years, is n times t, because n is the number of compounding periods per year times the number of years gives you the total number of compounding periods, like there. Okay, now the growth formula becomes u sub n equals u sub 0 times 1 plus I, so this r divided by n is just I, and this is raised to the power of small n. This is the number of compounding periods in total time as your money as your investment grows in the bank. Okay, now we will make a very clever substitution here. If I substitute n over r, and if I substitute it by a, then you can see that this formula here is u sub 0 times 1 plus, and you see r over n is the reciprocal to n over r, so it has to be 1 plus 1 over a. So if a is n over r, then 1 over a has to be r over n, like that, and all that is raised to n times t. But if I know that a equals n divided by r, it means that n is a times r, ar. Okay, so instead of n, I use ar, and add this t here. Okay, like this. So I can rewrite it a little bit and do it in the following way. It's u sub 0, now use the square bracket, 1 plus 1 over a, all to the power of a, like that, and all that to the power of r times t. Let me remove this, r times t. Okay, and this is the formula that we had to show that is true, this one. So it has the square bracket and this exponent here. What I used were just simple power laws, that if you have the power of the power, you multiply the exponents, like that. Now, what is interesting is this interior part here. This what is in square brackets, because it depends on n. As I increase n and have the constant r, which r means the percentage rate per year, which is a constant, say 6%, r is constant, and as I increase n, as n is increased, for example, as n tends to infinity, then it means that a has also to tend to infinity. So this bracket, this square, the content of this square bracket changes as a is increased, or as n is increased, to larger and larger numbers, and it should tend to some value. So what does it tend to? What is the value this thing here in this square bracket tends to? And this is what we learn in the following step of our investigation. So in part 4, for continuous compound growth, the number of interest payments per year, n, gets very large. Very large means that it tends to infinity. Explain why a gets very large as n gets very large. I already did it. A is the fraction n over r, and as you increase n and have a constant r, the answer, the result of this calculation increases. So a has to increase as n increases. Now, copy and complete the table giving your answers as accurately as technology admits. So again, this time I'm going to use Geogebra to calculate this number for each of these values of a. So to do it, let me go back, and now let me choose a new file if possible. I'm not sure if I can do it. File, new. I will not save this one. Here it is. I have a new file, and I will just create a column for a, and this column for 1 plus 1 over a, all raised to the power of a. So this is the table that I have to study or fill in our investigation, and the values of a increase 10 times each time you move from one row to the other, and they start at 10 and end up at 10 million. So, okay, let me start at 10. I have 100, 1,000, 10,000, 100,000, million, and 10 million, like this. Okay, what I have to calculate is the value of this expression as A increases to larger and larger numbers. So to do that, we will use just the calculating powers of GeoGebra. So I use the formula, this equals to bracket 1 plus 1 over, and instead of A, I just take A2, this cell, and all that raised to the power of the cell A2. Okay, so this is the number I obtain here. Again, let me increase in settings, let me increase the number of decimal places used to 5 decimal places. So this is the value, and now what is necessary to do is to copy this down and get these values here. Okay, so I will now copy those numbers into the table in the presentation, and then we'll talk about what it means. Okay, so here are the numbers obtained from my calculation in GeoGebra. I have them copied into the table here in this presentation in our investigation. Now let's move on to the next part. And the next part of this investigation is part 5, in which you should have, it tells us, you should have found that for very large values of A, these numbers here in the table tend towards this fantastic number, which you already know is the number E. It's the natural base of the exponential functions. And as you see, there is a correspondence 2.71828, which is fantastic. You can see it here. And as you increase the value of A, this value of this expression tends towards A. So we can say that as A tends to infinity, then the 1 plus 1 over A to the power of A tends to E. Okay, so this is what we can conclude from the investigation. Now they ask us, use the key e to the power of x on your calculator to find the value of a e to the power of 1. So I don't know if I'm able to do it on my calculator here. So what I need is to use this, but I need to use shift to get there because it's e to the power of something. Okay, so I take shift, this button here, and write 1 and equals, and what I get is this answer. Now you see what you get is 2.718281828. So this is exactly the value of E, and there is the correspondence between this result and the value of E in the calculator. Okay, so e to the power of 1 is exactly this function, and since this thing here is e to the power of 1, so what is this entire expression in part 3? Well, it has to be u sub 0 times e to the power of 1 to the power of rt, and you can see yourself that it must be u sub 0 times e to the power of rt. And this is exactly the formula used for compound interests. So r is the compound interest per year, and t is the number of years for which you want your investment to increase in the bank. So for continuous growth, u sub n equals u sub 0 times e to the power of rt. This is exactly the formula I showed you a sec ago. Now here is the explanation of the parameters. U sub 0 is the initial amount, U sub n is the final amount after the compounding period ends, R is the annual percentage rate, and T is the number of years. Use this formula to find the value of $1,000 investment as invested for 4 years at a fixed rate of 6% per annum. Okay, so if I want to do that, U sub n is going to be $1,000 times e to the power of 0.06 times, and it's 4 years, times 4. So if I take my calculator and use this function, it should be 1000 times, now use this shift key and e, and now in the exponent I write 0.06 times 4. Okay, like this. Okay, and this should be equal to, and it says it's equal to $1,271.25 dollars. And again, instead of equal sign, I should write approximately equal, because this is irrational number and I can't express it completely precisely. Okay, you can now do your homework and check whether this gives you the corresponding answer to the part 1 of our investigation. So in part 1 we increased the number of compounding periods during 1 year to very large numbers. The question is what you get by this formula corresponding to these numbers obtained in these 6 scenarios? So try to check it. Instead of 4, you have to use 1. Okay, so let me do it for you. So U sub n is then going to be $1,000 times e to the power of 0.06 times 1. So this is approximately, so let me check it, it should be 1000 times e to the power of 0.06, like this, okay, equals, and it is 1061.836547. You saw that we got $1,061.83 in our Geogebra spreadsheet, but then we lost the precision and it started to decrease, but there is a correspondence, a very nice fit. So that's it for this investigation.